All right, thanks for coming. My name is Pramod. I work for ThoughtWorks, doing a lot of database-related work, not necessarily like DBA type work, but how do you store data, what do you do with it, how do you use it, and for what purpose, and what are the most efficient ways of storing, taking them out, and refactoring them over a long span. Because applications come and go, so over a span of the company itself, like don't think application, the company itself, the data is valuable. So the application can come and go, but the data has to survive so that you can use it properly for further analysis and all that kind of stuff. So over the period at ThoughtWorks, I have written a couple of books, one of them being refactoring databases. So in a mature database, how do you refactor it and that kind of stuff. One other being how do you do databases and continuous integration. My latest book, along with Martin Fowler, is NoSQL Distilled, because we think the NoSQL movement is come to a stage where a lot of people are thinking about it and thinking about how to use NoSQL. So this book gives you an introduction in the sense that how do you have to change your mind when you think about NoSQL. Like you can't apply the same modeling things you did with RDBMS to a NoSQL technology and hope that it will perform better, right? Just because it's NoSQL. So the way I like to do this is if you have questions right there, then ask so that we can have a conversation instead of me just dumping a bunch of content on you, right? So we can tailor it to the way the questions are going instead of just following slides. So whenever you have a question, just ask. And if you don't understand any terms I'm talking about, just ask that too, like I don't understand what you're saying or whatever, right? Okay. So the first question is why NoSQL, right? So we know schema changes are hard, right? It's not easy, especially if you are in 24/7 kind of environment, large data sets, you want to rename a table, rename a column, add a column, remove an index. It basically locks up your database, and then you have to basically bring your app down, or people do this master-slave kind of thing, a lot of juggling around just to make that schema change stuff work. Right? There's an impedance mismatch, so we develop in objects, but we store in relational tables. That creates all kinds of interesting things. The ORM layer, the way you're thinking about it, or searching patterns change, and all that kind of crazy stuff happens. And because of which the code gets really complicated, and changing code for changing requirements then becomes hard. That's where schema change affects this impedance mismatch, right? Then the next is like we are used to thinking about integration databases, like there are a bunch of applications who are running on top of a database, and then the database becomes your bottleneck because if you change something for your application's database, it affects everybody else, right? So this is how we are stuck on this side here, because the integration database is where you move information around instead of going through the web service layer or a RESTful layer or something like that, and then the application can decide what to do with the database, right? So if you are on the right side kind of a situation, then your application can decide what to do with the database, refactor, change, redesign, whatever it needs to do without affecting the external customers of the data itself, right? So in the integration database model, if you change something for your application, most likely you're going to affect others. And that fear of affecting others stops you from doing things to the database or doing better things to the database, right? Then there's also this running on clusters. So like running any kind of RDBMS on a cluster is a pain. Like it's not that easy, it's expensive. Like Oracle 8 application cluster will cost you somewhere upwards of 7 figures, right? So running on clusters is really hard in an RDBMS. Not hard as in technically hard, but financially also, right? And nowadays with the whole web thing coming up and there's people wanting to track everything or all kinds of data, there's this whole notion of unstructured data, and the structure of the data itself keeps changing on you. So do you go and refactor the schema to fit to the new structure? How fast can you do that? That's again in question, right? And also there's this rate of growth, like there's the RDBMS capacity planning, whatever DBA types people do, they believe in this or they plan for this linear growth, like 40% growth every year, let's plan for that, have a SAN in place and all that kind of stuff. Nowadays, rates of growth are totally skewed because sometimes your product may go hit viral and in 2 days you'll have like terabytes of stuff coming at you, and in a month or so something new comes and people don't visit your site anymore. right? So that happens, and the rate of growth is up and down. So you need to think about technologies that can scale to that model of going up and down or going up very fast and that kind of stuff, right? So the rate of growth is also important. So having said that, let's go into this thinking about how do you model for this NoSQL movement. So right now, don't think about key values, documents, anything like that. Just think about your object, how you are modeling that object, and how the data in that object is gonna, like this is generally how your object model would look like, and let's take that object model, and this is how your data would look like in the database, right? So think of the first impedance mismatch slide you saw, and this is what is happening, like the model is being reflected as rows in the database, right? It gets complex pretty fast, and has, like Eric was talking about this, like in the cab we just came in, he was talking about this unbounded, like relations are all over the place and it doesn't get bounded. You can keep traversing as far as you want and it doesn't get bounded pretty properly, right? So that model creates all kinds of code complexity as well as lots of ORM headache, right? There is actually a paper which says like ORM is the Vietnam of computer science somewhere. So maybe that's a good read to do. But that's where this whole notion of aggregate model comes in. Like Eric Evans talks about domain-driven design. Think about the domain first, and then you can think about how to store that data in different ways, right? So in this here, we are saying the customer is aggregate as well as the order is an aggregate. So having taken that, you can then come up with a JSON representation of the aggregate itself, right? So we have customers with the ID of 1 and the name of Martin and a billing address of something. And in the orders aggregate, we have the order itself, like all the orders the customer ever placed with all the dependent things embedded inside it, right? So once you start thinking about in aggregates, then you can also start thinking about how these aggregates are to be related, because sometimes you may look at a customer and want to get all their orders, or sometimes you may want to look at an order and get the customer's information, right? This is where you can also need to think about options of how much do I get data by reference and how much do I get by embedding, right? So in NoSQL, a lot of people talk about embedding data as well as referencing data, right? And these references are not enforced by any NoSQL product. Like if, for example, here I have a customer ID of 1, and in the customers I have ID of 1. If you put ID 2, no, nobody cares. Not like relational database where somebody, like if you have a foreign key hopefully defined, then the database will barf at you saying foreign key doesn't meet the requirement. There's nothing like that in NoSQL. So you have to think of that too, like references can sometimes, if your data is not set up or there's a bug somewhere and you have wrong references, nobody's going to come and tell you that this reference is invalid, right? So you have to see how you can do that. But once you do this, then life becomes a lot easier, because now you're thinking in aggregates, and that aggregate itself can be moved around without having to worry about where data for the dependents comes from, because that aggregate itself is a self-contained thing, right? So think of like having to set up like test data in your database, right? In RDBMS, you would say, oh, I need order. That means I need 1 row in order table, 4 rows in order items, 5 rows in product, 1 row in customer, 1 row in, you have to go down that chain. Here there's no chain, there's a JSON and that's it, right? That is self-contained. So that simplifies a lot of thinking. Right? So you can have different aggregate models too. Like in the previous aggregate model, we had the customer as well as the order, right? You can also go down one more path of customer being the highest level aggregate that embeds other aggregates inside it, right? This is where NoSQL also will help you, because you could do rapid prototypes of this. You don't have to come up with the model that matches you perfectly in the first iteration. You could do multiple turns on this, and then as you grow, you can think about like, okay, that aggregate model suited me better than this one, or maybe this is where this is lacking. I can come up with a different aggregate model and things like that, right? So you could choose that, and then now the JSON totally changes. Is once you do JSON get, everything comes in it, like the customer, all its orders and everything is in one packet coming back from the database, right? So you don't have to do multiple gets on the database, right? So here's like a easier image of the same thing. Let's say, for example, you had a customer as a key, right? And the value is an object, and inside that value object, there are multiple objects like the customer object, the billing address, the orders is a collection of orders, and the order itself has a shipping address, the order payment, all of that embedded inside the key of the customer ID. So once you get the key and its value from the database, everything is inside. You don't have to go back to the database again at all for anything else, right? And the application can then break it down, put it into your objects, and then do whatever you need to do with it. You can also have references within the aggregates. So for example, here we have a customer ID and the value is object about the customers. It has a list of references to the order IDs, right? And then there's also an object for each order within that list, right? So whenever I place a new order as an existing customer, I create a new key for that order ID and persist the rest of it. At the same time, I add to the list of orders in the references for the customers, right? So that's how I do a double write, one to the orders and the other to the customer, just append the list of order IDs. So obviously this has some downsides because, as you know, most NoSQL databases don't support ACID transactions. So your order may get returned and your customer write may fail, then you have reference problems. Or your order may fail and your customer may get returned. So you have to do this on the application side. If the write fails, retry or something like that, or make the other guy fail, something like that. You have to think about this at the architectural level. You can't just hope that it will work, right? So this is an important trade-off you're making while making the choice of splitting the aggregate, right? So you can use the same kind of references with JSON documents. Here's a JSON representation of the same thing, right? So what does aggregate orientation gives you, right? One thing is the RDBMS themselves are not aggregate aware. Like RDBMSs have this concept of materialized views, but materialized view is still a row, right? You can't have a materialized view with one customer ID and 3 addresses. You will need like 3 sets of columns for addresses for that to show up properly. You can always take XML and stuff it into a column in the database for a key and a value in the RDBMS, but then you're making the RDBMS behave like a key value store, right? So that's the difference between aggregate thinking and non-aggregate thinking or relational thinking, right? Once you start thinking about aggregates, the whole notion of ACID compliance kind of becomes a lesser priority, right? Because now it's a single read and a single write. You need ACID in the database like RDBMS terms, mostly because you're writing to 4 or 5 different tables. Like think about persisting an order. You're writing to the order table, you're writing to the order item table, maybe you're writing to the stock inventory table because you did a subtraction. So those many writes, that's where ACID becomes very important, because if any one of them fails, you want to fail the rest of it, right? Here you're writing a single aggregate. If the aggregate fails, everything fails as it is, right? Because it's a single aggregate, right? So that's where like a lot of people have these questions of, oh, no SQL, no ACID. I have questions, how can I use this? So switch your thinking in terms of aggregates, and that will make thinking about NoSQL a little bit easier, right? Once you go to the aggregate model, running on clusters becomes easier, because now it's just an aggregate, it's a self-contained unit. You can store wherever you want, right? 1 server, 10 servers, 1,000 servers, doesn't really matter, because it's just one aggregate gets stored wherever. In relational databases, like clusters make it very hard, because then you have to think about related rows, where they go and that kind of stuff. Here the aggregate itself is a single unit that can be pushed wherever you want it to be pushed, right? So now coming to the databases, like key value stores, document databases, and column family stores are all aggregate based according to us, right? So a key value store just has a key and a value. The value is the aggregate. In the document databases also, you have a key and a value that goes with it. The value is understood by the database. Sure, you can query on parts of the value, but it's still a key and a value. The value is visible to the database, right? And the column family comes in the same model of there's a row and the row has columns, but the row still is an aggregate at the aggregate level, right? So when you start thinking about NoSQL databases, think whether you are in the aggregate camp or the non-aggregate camp. And then you will have to also think about like graph databases, which are a totally different beast altogether, right? So we'll talk about each three of these as well as talk about graph databases, right? So in graph databases, the modeling totally changes, right? Each node is on its own, and the node has relationships with other nodes, right? So think of like a simple e-commerce app where your customer actually purchased a product, right? And he was billed to a given address. He was part of order and that kind of stuff. And these relationships have names, and those names can have values too, like a key value pair attached to that relationship, right? So you can do very rich domain modeling on these nodes as well as the relationships, right? And that's where traversal becomes very important. So if you are really interested in connected data, like how the data is connected to each other and what does the connectedness give me in terms of the intelligence about the data and the actions people are doing, that's where you start thinking about graph databases. An easier example to think about this would be like, let's say you wanted to look at knowledge sharing within a given organization. Like let's say your company, you are thinking about analyzing how people share knowledge, right? Or how people interact with each other and that kind of stuff. You could easily go through your email archives and see who wrote to whom on what topic, right? And in what locations they were. You can do all kinds of modeling and then decide like what is the most highest bandwidth between two sets of people, all right? That can be done using graph databases. What that gives you is like what are the blockers, what are the enablers for better communication, right? So that's where you would use graph kind of modeling, right? So the key points is inter-aggregate relations are hard to maintain. That's where I was saying like if you use references and one of the operations fails, then you don't know which one succeeded, which one, the references may be out of sync. So you'll have to do that on the application side in the sense if something fails, rewrite it, or fail the whole transaction or fail the whole operation on the application side, right? Schema-less, everybody likes schema-less in NoSQL, but the schema is still implicit in your code. That's the biggest trip I have seen people do is like they'll think, oh, schema-less, I don't need to worry about schema. A couple of iterations later, they can't get to the data because the schema has changed. Now some of the rows or some of the documents that are returned using the old schema cannot be parsed anymore, and that kind of stuff. So if you're thinking, hey, schema free, I don't have to worry about it, stop that thinking right now, right? You have to worry about it because it is schema free only in the database. The schema is in the application side, right? So we'll talk about a couple of techniques on how to do this schema migration, multiple object versioning, and that kind of stuff in the database, right? And like I said, graph databases work especially with complex connected data that you want to analyze. So having said that, let's go into the details of each of these types of databases, right? So a key value store is a simple key and a value, right? Let's make this work. It's a simple key and a value. The database doesn't really care what's in the value. It could be a JPEG or it could be a JSON or a XML. It doesn't really care. It doesn't even know what's inside. You put a key along with the value in the database, you get a key and a value back. And it's your responsibility to decode or decipher whatever is the content, right? So if you are like a car kind of a company, or at least thinking about doing something with cars, like a key, which is a vehicle identification number, is a natural key for that value, right? And then inside that, you could store all kinds of stuff, right? It's a natural extension for key value. Some of these products are Riak is an example, Redis is an example, Voldemort is an example, Memcached, a lot of people know Memcached is an example of a key value store, right? When doing key value stores, you need to really think about key separation or like key namespaces. If you are doing like, for example, you want to have multiple objects, one for the vehicle identification number, when it was bought, what was the things that were installed on the car, if that's one of your key and value. If the other key and value is what all oil changes, what all times I did oil change and maintenance on the car, then your key can collide. So you need to design your key properly. It could be win underscore new or win underscore factory installed options. And the second would be win underscore maintenance, something like that. You need to think about the key or the namespace design when you're talking about doing the key. Some of the products like Riak have this concept known as buckets. So you can create separate buckets with the same key, right? So one bucket would be called as factory installed options, and that would have the same win in it, but the value would be the same thing, right? Would go in a different bucket. So that's a key space separation technique that they have, which is called buckets, right? But you have to think about, like, if you are storing multiple objects, you have to think about how you would do those key separations. So we like to compare back to our known knowledge, right? So like if it's Riak, that would be, or like a bucket, that's where I was saying bucket, right? So that's what the terms on the Riak side would be, and on the Oracle side, that's what the terms would be, right? So there is one key, one value. A value is opaque to the databases, right? It doesn't really matter what's stored, and it's just like hash. So if you are used to using hashes in Java, it's a key and a value, and whatever is stuff in there doesn't really matter, right? And because it's an aggregate based model, then you can distribution becomes easier. Yeah. So let's move on to Mongo databases. That's what document databases, mostly people think about Mongo, right? But document databases, there are many of them. Again, like if you think the model is the same here, like I was saying, key value and document databases, the only difference or the big difference is that the value is understood by the database, right? And they get to this fact by forcing the value to be either JSON or XML. Like MarkLogic is an example that has XML as the actual content, right? So again, going back to the same example, we have our ID as a vehicle identification number, and the document is basically a bunch of car facts, right? Like it's a JSON here, has a bunch of things. Like document databases here are MongoDB, Raven, right? And then you have CouchDB, Terrastore, OrientDB, right? So in, like, for example, if you take MongoDB, in MongoDB you can have this underscore ID that is the actual key of the document, and if you don't provide one, the database will actually create one. If you provide one, the database will override that value and give your own key to the underscore ID value, right? So here is an example, like for example, row ID in Oracle would be underscore ID. But in Oracle, you cannot change the row ID. In Mongo, you can change the row ID, underscore ID value by overriding it with whatever you have. Of course, a lot of times people ask, why would I even override the underscore ID? Because the database is providing it to me. Sometimes, like in high performance situations, the index that MongoDB works off of, it's best to have the whole index in memory for it to have proper scans. If your index is not all paged in memory, then MongoDB sometimes does not perform as well as you want it to. So you can take over the underscore ID space in memory by giving it your own key. So you are saving the space in memory by using the underscore ID for your own key, right? So for example, the underscore ID I think is a 16-byte value or something like that, the default one provided. If you had your own ID, which was the customer's ID or whatever, if you replace that, swap that, you would basically save the index space that fits into RAM for that underscore ID value, because you would have an index on the customer ID on the document anyway to access those, right? So think of that when you do index design on MongoDB, right? But again, going back here, the instance is a MongoDB, a schema is a database, table is a collection, row is a document, and the row ID is underscore ID, right? Again, there's one key, one value. The value is visible to the database. So you can do intelligent queries on, in the JSON document, find me all the documents where the name is like, all of that can be done, right? Like a standard RDBMS query. The value can be queried. You can put JSON or XML documents in them, right? Any questions so far? I'm doing pretty good? Okay. So let's move on to column family stores, right? So column family again has ID and a column families, and these column families have like a row that has columns inside it, and each column has a key value. So it's kind of a hash inside a hash kind of a model, right? So usually a column family data model is very hard to grasp in the first go, but think of it, a row as columns, and columns have key values inside them. Kind of makes it a little easier to understand, right? Cassandra, Hypertable, and HBase, Apache HBase are examples of these products. One thing to think about this is when you write to a column, the column gets versioned. It doesn't get deleted, right? So let's say the previous value was name, and the value was John, and the new one you write is the name, the value is Robert. The John value is still around, it doesn't get deleted. That's why like data size grows exponentially, so you have to go back and do a repair on the database, like kind of like offline, that compacts this data, right? So you see this same stuff happening even in CouchDB, like data grows exponentially because it doesn't delete anything, it just keeps versions of stuff. And if you don't care about old versions, you just compact or repair the database and it just goes away. So if you see exponential rise in disk usage in one of these products, make sure you understand the repair or the compactation algorithms used by these things. In a column family database, like comparing back to Oracle, like an instance would be a cluster, a database is a key space, a table is a column family, and a row is a row, which is kind of all confusing, but that's how it is. The only big difference being in a given row or in a given table, all columns in the RDBMS are of the same type, right? So if you say int, it's all every row in there has to be an int. But that's not true with a column family database or Cassandra at least, right? So you can have the same column mean different things. That's what I was saying, each column has version data and you can expire them. You can even put an expiry date on them. Like let's say when you write John got changed to Robert, and you can put an expiry on John saying after 3 days this just goes away, and that's where you can show multiple versions if people wanted to like come back and then compare data and pick which one is correct, like manual intervention or things like that, right?
So
yep.
What's a real life example when you want to use a column family store?
Sure. Column family store, a real XIF example would be like you wanted to do real-time event writes, for example, right? So stuff is coming from the web, stuff is coming from your internal system, stuff is coming from your third-party vendors who are using your widgets or whatever. All these events are coming at you at a high rate. Then you want to just put like a REST service in the front and then write it out, because column family stores support high write volumes because they don't do any deletes. They just keep writing with new versions, right? And then the data size goes, and in the back end you can then compact them out, right? And you can also write different types of what I like to call them as like you are aggregating data online, in the sense like an event comes in and you put the event as is, but in the same transaction you then aggregate it saying, okay, count the number of customers, increment it by 1, count the number of products sold, increment by 1. All that kind of counters can be done real time, in the sense the moment the event comes. And then you can use that to display somewhere saying, oh, in the last hour 54 customers bought this item 302 times. That kind of stuff is a very good example of using column family, right? So onto graph databases. Neo4j is an example. Then we have Infinity Graph, OrientDB, and HyperGraphDB. A graph database can be used for anything actually, right? So it doesn't necessarily mean it has to be a graph type of a problem, because each node there can have its own key value store, right? Each node can have multiple keys, multiple values, so you can stuff a bunch of data in there. Not just the node, even the edge or the relationship can have its own key values, right? So let's say, for example, I am related to him, and I could have like, when did I know him? What was the last time I met him? What was the last time I had dinner with him? All that kind of information can actually be put on the edge, not on the node, right? Because that's the property of the edge, not of the node, right? Because my property with him can be totally different because that's the property of the relationship, right? So then you could do intelligent query like, give me all the people who I had dinner with in the last year or so, or in the last year that are related to me, right? That's known as a graph traversal, can be done here. Like for example, you can do a query here, give me all the nodes that know Martin, right? And like NoSQL Distilled, something like that, right? So you are not only querying the nodes, but as well as the relationships. Does that make sense? Right. So graph TOS it's basically a multi-relational graph. Relationships are first-class citizens. Like in RDBMS, we think it's a relational database, so its relations may be important. It only enforces relationships. It doesn't let you traverse relationships. You have to write complex SQL to traverse the relationships. It doesn't let you do what graph databases let you do because you can traverse relationships. The way they achieve this is by writing the node properties as well as the edge properties in separate storage. That's why it's more efficient. For 10 nodes, the query time, and for 1,000,000 nodes, the query time is the same in Neo4j because they write different information. It's optimized on write time, not on read time. In RDBMS, you optimize the write, but not optimize the read because your traversal, if it changes, you have to write new SQL, right? So there are also a lot of traversal algorithms available that you can apply to the graph itself, right? And nodes and edges can have data, which is basically key value pairs, right? So let's see some good usage cases for these key value stores, right? So key value stores are good for session storage, like browser session, whatever you want to store across session caches. Profiles, like I have a user ID, for example, a blogging platform or like a e-commerce web app or something like that. I have a user ID. I want to get his profile, like name and anything else, email, shipping address, billing address, whatever it is. It all can be stuffed under the user ID as a key, and everything else is a value, right? You get one, everything comes with it. Similarly, would be preferences. So like screen color, font size, or whatever else you want to have preferences can all go under the same. Or the shopping cart is a good example, like a scalable shopping cart. Like for example, if you use Riak, you could put the customer ID underscore order ID as your key, and the value would be whatever people are buying at that time, and have that thing saved, so you can get it back when the customer comes back because of losing session cache or something like that, right? In a document database, you could use it for event logging. Prototype development is a big way to like get your iterations out without having to think about like schema or deployment complexity or all that kind of stuff. You can have rapid prototypes out, and once the prototype is mature, then you can think, okay, how do I do this? Like what kind of different technologies do I need for aggregates, right? E-commerce web app is a good example. For column family, like large write volume, like I was saying, you could use it for content management, you can use it for e-commerce applications, right? And the graph databases can be used for connected data, routing, like how do I route my delivery truck from point A to point Z with 3 stops in between, what's the most efficient way? Then you can have the stops as nodes and the distance between them as your edges, and then you can just ask the graph database to give you the shortest route, and it will give you the shortest route without having to think about it, right? Location services, you can even run recommendation engines. For example, customers who buy this product usually buy this other product too. It's very easy in the graph database sense to say that, right? So those are some general use cases of the 4 categories of databases that we are talking about, right? So obviously, coming back to the schema-less, so we did say databases are schema-less, but the schema is implicit in the sense that your code is saying, okay, put this JSON in there, and when I read back, I need to be able to parse the JSON, make some sense out of the JSON, convert it into my Java objects or whatever other objects you got, and then work with it. If the structure of the JSON changes, then obviously it's not going to map to your object. So that's where the friction is. Instead of in the database, it's now at your mapping layer, right? So obviously, when you say schema free, I can change the schema whatever way. It doesn't mean you don't have data migration, all right? So imagine you had a customer object that had a name and address as its 2 fields. Now you change the name to say customer name, for example. So the new ones that store it as customer name, but the old ones that are there are still there as name, right? So when you try to parse it back, you need to parse both of them, right? So if there is customer name, use that. If there is no customer name, use name, right? So you have to have this pattern in your JSON parser that says, okay, these 2 map to the same thing, right? So that's where data migration comes in, is let's change every document I have to be customer name instead of name, right? That's an expensive proposition and goes back to the same relational model of like, if I change a column name, it affects every row, right? That's where people are moving away from RDBMS because they don't want to deal with it, right? Deal with changing the column name and affecting everything. So you can do techniques like lazy migration, right? So in the sense, when you read both the columns, but when you write it back, you write with the new one, right? So that you're basically upgrading one document at a time or one value at a time. Basically, when your app reads, it reads both of them and does the right mapping. When it writes back the new way of doing things, right? That's one way of doing it. The other way of doing it is writing the same logic offline, and it basically goes one document at a time and doesn't affect anything else. And the new code can then be deployed once the whole thing is done, or can be deployed in parallel in whatever other ways you like. It all depends on your data size. If you have like petabytes of data, then it will take a long time. So you have to think about how both can go parallel. If you don't have that much data, then you can maybe run it offline and then deploy the new code, right? But your new code needs to understand the data structures so that they can parse them properly, right? Don't just go with the feeling that, oh, schema-less, I can change, doesn't matter. You will lose data. You will lose data in the sense you will not be able to read the data that's there because the structure has changed, right? Because schema is implicit in code. And when you change the implicit schema in the code, your data also needs to conform to the new schema. Right? Some of the projects where I have worked on, the way we have done this is written probes in the application code itself that would just go pick random 4 documents and see if it conforms. And if it doesn't conform, we would come back and say, okay, the database doesn't match what I'm looking for. Then we would go back and then write like offline one document at a time kind of a thing. And it would go back and change all of those. Right? That's one way to just report saying, okay, the application and the database doesn't kind of match. Right? This is a very good thing about NoSQL is all data doesn't have to be migrated at the same time because different documents can have different structure. So I can do one at a time and doesn't really affect availability or any kind of other scenarios. Right? So that brings this whole notion of polyglot persistence because we think the application needs different kind of storage. The storage for order persistence is totally different from recommendation engine storage, is totally different from session storage, is totally different from any other kinds of reporting, ad hoc reporting stuff you need or care about, right? So why do we use the same technology, same storage engine for all of these needs, right? So why not use what is suited for that particular purpose to do the task instead of just shoehorning everything into the same thing, right? It can be across the same application or it can be across the whole enterprise. For example, I would have a recommendation engine running for the whole enterprise in the graph database and slap a service on top of it, and it could be a service for the whole enterprise that says this is how you do recommendation engine. Or I could do the same thing that a session storage, here's a session storage service, you do a get and a put on the service and we will manage everything in the back. And none of the other apps you'll write in your whole enterprise don't need to worry about session storage anymore, right? You could do that kind of service too, right? It doesn't have to be, you don't have to think about only in the context of application. You can extrapolate it up at the enterprise level too, right? So that's where the key concept of encapsulating data access through services comes in, is I just have a service that does whatever it's supposed to do. And in the beginning stages, just as a proof of concept, you could even write to a disk or something else and slowly then migrate to a better storage, like using a key value or something like that, or whatever makes sense to match the needs instead of writing all to the same database, right? So here's like a simple way of showing it, right? Those are services sitting on top of databases, right? So session storage will go to a key value store, order persistence may go to a document, you are reading inventory and price and all that kind of stuff from a relational database, which is legacy. That's where all your backend systems are write to, and you could write the customer recommendation stuff coming from a graph database, right? You could also do, there are multiple models of this. This is not the say one and only model, right? You could also do like your shopping cart data can still go here, session data can still go here because that's what you're used to. But searching is becoming a pain for me because I have to write complex SQL just to find data. I could pump the data through like a Solar and do that kind of stuff because data is going from here being fed here and I'm just posting search requests on top of, right? That's one more model. So you can have all kinds of model here. Think of that like I can just have this and with this also have one more for this graph stuff where data is being fed from the RDBMS to a graph database and I'm just doing queries against the graph database for recommendations, right? That can be done. You don't have to go crazy like this in the first go. You could do slower iterations on that too, right? So here Martin actually blogged about this polyglot processing. This is totally speculative. Use everything under the sun kind of model here, but we are doing like user sessions in Redis, financial data that's already coming from backend systems in RDBMS, shopping cart is going to Riak, recommendations is going to Neo4j, product catalog is coming from Mongo, again ad hoc reporting is going to RDBMS, analytics is going to Cassandra, user activity logs are going to Cassandra, right? So this is totally like use everything and make sure everything is persisted using the same thing, right? Obviously the final question you would have is how do I choose, right? There are 4 broad categories, 20 plus products, what do I choose, right? You can choose for programmer productivity, right? So what will make my friction of saving this and getting back the easiest, right? You can choose for that. If taking the product to market is your single most biggest concern, like let me prove if this works, then you can choose for that. You can choose for data access performance, right? Like for example, if relationships and recommendations are important, then you would choose for performance, right? Today I have 10 customers, tomorrow or a year from now I have 5 million customers. Will my recommendation engine scale? All right? You can choose with those questions in mind. You can choose with, hey, I am working already with this, like why even think about new stuff? That's a choice you can make, right? You can also test the expectations, right? So I did this project for the Democratic National Committee, which is the Democratic Party's headquarters kind of stuff in 2010-ish. And we actually ran tests, like all kinds of tests, because most of this is open source. You don't actually pay a dime to install and run this, all right? So we installed this stuff, did whatever we needed to do, and we were supposed to provide 1 million hits per hour proof that it can handle that amount of volume. So we actually coded, ran this, ran performance test on it, and then tweaked and then chose that, okay, this works, right? So you could do test your expectations, right? So like we generally choose based on reading some stuff somewhere and making sure that that matches with our context or our problem set. And if it matches, we choose. Sometimes it doesn't match because somebody is talking about like a web app and you are building something else. Then actually code it, like do a short spike on it and performance test it and see how it works, right? Because it doesn't cost anything to download and install Cassandra or Mongo or Neo4j or anything as for that matter, right? It doesn't cost you anything other than your time, which is actually very good because you are investing your time to find out if the product is good for you, right? Like I said, they are all open source. You can try all of them and see what fits where and then test your expectations, and then you can write performance tests against them. Like in the DNC project I mentioned, actually every check-in actually went through like check-in, then we did like this code analysis, then we did unit test, then we did integration test. After that came the performance benchmark test, which basically took the code, deployed it against a production test environment and ran the whole thing for 2 hours. And we would say, okay, this code passes that, and then it was deployment ready at that time. So you could do that kind of scenario too, right? That's all I had. I know I was said an hour, but it's done in 45 minutes, which is always good. So that's the book. That's the other books I was saying. I write here, so if you want to go read what I write, or if you want to message me, ask other questions, you can go for that too. So Any questions, anything? Yeah?
I have a question about this schema-less. You said that the schema information would be in the application, not in the database anymore, but I would expect my database to let me access the data by certain search criteria. Now, that would contain schema information.
Right.
Does that mean that maintaining search indexes in your picture would be part of the application now in this setup? Or?
Sure. So there are different things. Like in key value, you cannot actually search by value at all, right? So your application needs to take that value, put it into a different search index like Solar or Endeca or something like that itself, right? The database is not going to do that. Nowadays, Riak is also supporting index search kind of product that sits on top of the database that indexes for you. In the document store, you can actually query the value, right? But let's say your query was written for the JSON document containing the customer's name to be called, the attribute to be called as name, and then you change it, right? You change it to client, for example. Then your query that you had written will need to now know the new stuff, right? That's where the difference comes in, is the database can index the name column for you, but you change the column itself to be called client now. So the index doesn't even hit the client column at all because the index is hitting the name column. So now you need to create one more index for the client column or the client attribute in the JSON column, right? And then you would be able to hit, like you search for name as well as client, and then you would find one of them.
So that means that the information about the schema is not in the application alone, it's also in this index layer of the database.
Yes, yes, yes. And that's where like JSON document are self-contained schema definition documents, right? So every JSON document has its own schema defined because you can traverse any JSON document by using Jackson JSON library or anything like that. You can do a dynamic traversal of it. But if you change the document, the index definition doesn't change along with it because those are disconnected things, right? So you change the document, you stored a new document. The index was defined on the old document using the old name. The index doesn't care, the old name is still there. Even if any of the document in your whole database doesn't have that column, the index still doesn't care because you defined the index on the old column. That's what it's doing, right? So that's where the disconnect comes from, thinking is schema is in the application and it affects other things you do along. The same thing applies to relational databases too, right? You change a column name, you don't change it in the stored proc, you don't change it in the trigger, stuff is going to affect you, right? Similarly, it will affect here also. That's what I'm trying to say is don't just think schema-less means I don't need to worry about schema. You have to, right? Yeah.
On your last slide, you mentioned the testing part, how to choose the last part.
Yeah.
And that might be a good catch if you have application that you want to migrate from RDBMS to something else. But what do you do if you are on a greenfield approach and you don't know what the data would actually be in 12 months?
Sure, and that's actually a very good place to start with. Like you are domain modeling, right? So when you domain model, think about the aggregates, not about the storage, right? And when you do that, you can extrapolate saying, okay, given today, if my product goes viral, I will get this amount of customers or whatever. You can make up the customers and extrapolate and test for it, right? Let's say today I have 10 customers, like first day of launch I get 10 customers, and I'll extrapolate, in a year I'm going to get 2 million customers. Each one of them is going to order 4 products every other day, right? So you can put that kind of calculations and then calculate what kind of transaction rates do I need to run. Right? So like the Democratic Party, I was saying, we didn't have any real data. We made up data in the sense like what are the ratios, what are the hits that are going to come, what is the kind of randomness we are looking for. So all of that has to be calculated. Like
so you model your application up front in the domain language?
Yes.
And afterwards you choose which database to use?
Yes.
Okay.
Yes. And you don't even upfront model to the like nth degree. You just need, okay, this is the first iteration I'm looking for. Model it for the first iteration and then keep iterating over it. Because the first go, you may come up with the aggregate model of like X, and in third go, you may come with totally different aggregate model. That's as you iterate, you will find different options. Yeah.
Okay.
Okay. We'll come to you.
refactoring databases book is about relational databases.
Uh-huh.
How's refactoring on NoSQL databases? Will you write another book on it? Or
I don't think we are at that stage yet, but there is certainly a lot of thinking that needs to be done about like how you change data, right? So a lot of times people will just like, okay, let's change it in the application, and then after like 3 or 4 days somebody complains about my order doesn't show up, or my this thing customer information is wrong, then they start digging back. So the first part you need to think about is how do I change the structures and make it visible across all the dependent systems. So a lot of maturity needs to come there. It's very nascent right now, so I don't think there are patterns emerging yet to write something about so far. Yeah.
Experience in operating these products? How mature are they regarding updates of the database? Do I need to update the data store, or does it work?
Like keeping them in production, is that what you're asking? Yeah. So most of these are like not version 10 or not version 11 Oracle kind of products, right? So you go with that mindset. There are a lot of like command line tools, right? Because there are now not much commercial vendors in this space yet. There's not many UI tools, but most of them are command line tools. Most of them are open source, so you can actually look at the code and hack it yourself too, right? There's also a lot of tools available that are plugins to these existing products, like Nagios has a plugin for Mongo, for example, right? So you want Nagios alert, there's a plugin that you can plug in. Mongo also has this MMS activity monitoring thing going on that can report on the cloud how your database is doing, for example. Or Neo4j also has like lots of other tools. In the commercial edition, they have this high availability cluster available and that kind of stuff, right? Different products have different layers or levels of maturity, and if you go with something that has a company behind it, like for example Neo4j has Neo4j Technologies, Neo Technologies behind it, so you can buy commercial support and that kind of stuff from them if that matters to some organizations because they want someone to call and do something with them kind of stuff. So that is possible too. But in production, most of the time, like I've run Mongo in production for almost 3 years now at one client, and like recent client, it's been like 3 weeks since we have put Memcached as well as MongoDB in production. You can like mostly do all puppetization of these. These are very easily scriptable. That's one switch from the relational. Like relational was all UI based. Like installing Oracle on a command line is hard. Like try to do headless Oracle installation, man, it's hard, right? So you can do like Mongo, you can just download, unzip, and it runs, right? So think of that too. Like you can do a lot of Puppet kind of scripts on this. Yeah.
You just said I should first design my data in aggregates or whatever in my design model, and then decide which is my correct storage. But isn't it also that if I use a graph database, I need to kind of match my design so that it fits in this key and connections, nodes and connections?
Right. So
kind of like back and forth. If I kind of like I have a problem, it matches somewhat more a graph problem. So I choose a graph database, and then I put I have a model that really matches the graphing.
Sure, and I mean there are two big categories here: aggregate and graph, right? So when you're modeling, you will like within the first day know if it's aggregate or graph. That's kind of easy decision, I think, right? And then within the aggregate, then you what do I use? Key value, document, or column family is a more detailed discussion and discovery that needs to happen. In the graph, when you start modeling, then the graph modeling is a lot different than like relational modeling, because keys on the nodes, keys and values on the nodes, and keys and values on the edges, the names of the edges are like a discussion onto themselves. Like how do I do? Like do I do all as incoming relations? Do I do as outgoing relationships? How do I query? That makes the change. Like even in graph, once you come up with like a first version of your domain model and 3 or 4 versions later, your domain model may totally change on what you learned about the domain as well as what the graph databases support, right? Because a lot of times we go with like, let's do all the leaf edges pointing to the branches and higher as you go. And after some time, you may realize, oh, I actually want to go top down instead of bottom up, right? So you'll have to switch every edge. That's one interesting thing about graph databases is if you change the name of the edge in your code, all the edges will not change automatically. You'll have to go to every node and create the edge again. That comes with schema migration. So we have written this about in the book is like 2 nodes have an edge named as father of, for example, and you want to change the name of the edge to like dad of or biological father of or something like that. You change that in the code, the database doesn't know about it. It doesn't really care. So if you query for father of and query for biological father of, you'll not get the same nodes. You'll have to go traverse the database and make the same connections between those two nodes with a new edge and then delete the old edge. Does that make sense? Yeah?
So basically what you're saying is, I look at my problem, then I decide is it an aggregate problem, is it a graph problem, or is it maybe a SQL problem?
Right.
And then I kind of match my modeling according to this broad split.
Categories, yes.
And then I can say, okay, in the SQL space I have lots of products, in the aggregate space I have different types of products.
Yes.
And then I go into more detail.
Yes. Right. So you have to think about what is the context. What is the context you are solving it under? What is your problem, right? I can't just sit here and say, hey, use key value or use graph. It will be kind of stupid, right? For my part. Yeah.
Could you give an example for a use case where you wouldn't use NoSQL?
I mean, there are many use cases, right? So one is like your organization's capability to use NoSQL itself, right? NoSQL comes with a lot of baggage on its own, right? It's not like it's the panacea of. There are a lot of blogs around that says how we failed with NoSQL. There are a lot of blogs around if you go read that, right? That's where like thinking about your problem first, right? What you're trying to solve is more important than I have a project, I want to use NoSQL. The straight connection is wrong, right? So you have to think about what it fits the problem, how you are going to solve it, and what are the properties of that particular product that actually entice you, and what are the negative aspects that may affect you, right? So you have to think of those two and then make the decision, right?
Thank you.
Yeah. Like there's an existing, like for example, you have this product running in your shop or application running in your shop for like 20 years, it's working with relational. Don't go and change it to NoSQL tomorrow. I mean, that's a straight answer right there. Like, so try something new, greenfield is coming that is different in terms of the problem it's trying to solve. Then see if NoSQL applies there. Like, don't just go and change a legacy app that's already running to use NoSQL. Okay, maybe Maya? Time-wise, are we doing okay? Yeah? Yeah? Okay.
One more question.
Sure.
Coming back to the schema-lessness and the migration part, what are concepts to find out that I hit every node in the NoSQL database when I do a migration? Because I can imagine that when I have the JSON parser, which basically has a lot of compatibility code inside, it might get more complex and hard to maintain.
Yes, it will get complex. Like similar to like in the refactoring databases book, we talked about this transition phase, right? Old to new, and you have some transition phase in the middle. Like I'm going to drop this column in 2 months when all my code moves, right? So if that 2 months becomes 3 years for you, you will have a complex schema. Same thing will happen with your NoSQL store too. Like if you don't clean up fast enough, then you will have lots of these layers in the middle that say, okay, name, client, party name, and all are all the same. Then your code, the translation layer code and the JSON itself will become complex in the sense it's not cleaner. Similar to like any code that if you don't clean up regularly, it becomes dirty. Same thing applies.
Is there a concept of kind of like throwing the NoSQL database if everything is migrated?
No, you will have to do it yourself. Yes. Yes, there's nothing like, because the database doesn't really care what you store, right? For it, every document can be different. That's by design, right?
It's different from relational database.
Yes.
Because I know that column has changed. I can check the values inside.
Yes.
Query them, but with NoSQL, I understand that
there's no such concept yet. Yeah.
But depending on the technology, like in document databases, you could query for all documents that have a key name.
Yes.
So you can find all the documents that still have the old name in it. And
Yes, that we have to do it. That's what I'm saying. Like, you have to do something about it yourself. The database doesn't give you any like automated way of doing it.
There's no special functionality or special query for the document type.
Yes. So you will have to write your own query, like give me all the documents that have this old name in it, and then go through, iterate over them, and then change them or do whatever you need to do.
Have you seen an example, like you showed me an example in real life, that there are 3-4 different types of persistent stores in the same enterprise system, like the financial data in RDBMS, and session data and key value store, recommendations in the graph database, if you have it in the same company, the same enterprise system?
I have seen 3 of them in the same enterprise system, yes.
And does it scale?
Yeah. Yeah.
I mean, because of complexity and operational complexity and developer complexity, that you have to grab the different concepts as a developer, and as a operator, you have to operate as different systems.
You have to think about like how will you set up this. In the terms like developers need a local version of this stuff while they're developing. We do all systems using continuous integration, so the CI system needs to know about it. The QA system needs to have a different instance, right? So the first time we do this, we'll do like a Puppet version for the developer instance itself, right? And the second would be for the CI instance. From QA onwards, it changes a little. So that needs a different kind of Puppet system, because QA needs a cluster, because we don't want clusters introduced in production only. Like it needs to be introduced a little earlier, right? So you need to think about, how do I do this deployment? That's where the whole DevOps comes in, like put in more Puppet versions to deploy different kinds of systems. And you don't want a person manually sitting and doing this on different machines, right? So for example, you can add nodes transparently to these clusters. Like in Riak, you can just add a node and say, make it part of the cluster. You don't want a person sitting there and typing this every time you want to add a node. Right? So that's where you need to think about Puppet or some kind of script. I don't really care if it's Puppet or a shell script, but some kind of script that does it for you. Right? Even on a developer machine, right? We had in this DNC project, we had a Ruby script that basically went to the internet, downloaded the latest stuff, unzipped them, packaged them, and said, run. Here's your local developer instance ready to go. Right? So you could do that also. You don't need to actually like rely on a person clicking through or a person manually, like a document, Word document that says, go to this website, download this stuff. You don't need. Yeah. Yeah.
There's an interesting question hidden in that, the effort you need to put in to use a new database. We're currently introducing MongoDB, replacing SQL database, part of our application to Mongo. And the biggest overhead is not the developer learning MongoDB and using a different framework to persist. That's usually really easy. But then you have other systems that query the data, and now they can't anymore because they don't have adapters to MongoDB. Or they need to monitor, they need to install, all this kind of stuff. All kinds of people need to know.
Sure. There's the ops team that doesn't know about. There's the DBAs, they don't know about how to take backups of this stuff. Right? How do I take a backup? How do I restore? What are the other things that go with it? They don't know, or they need to learn, right? So that's all the other things that comes with it. The other option that you may have is like, how do I deal with data that is needed by this external system? And the external system usually is poking directly into your database and reading off of the tables, right? So that's where that integration database pattern comes in. And now you're moving more towards a service-based pattern. So in the meantime, what we have done in this current client is the application on the other side can just invoke a REST call, and the REST call goes back in the database, dumps a CSV file out, and that it can read the CSV file back up. Right? That's the integration pattern we used, is basically like a service invokes, returns, or gives it a CSV file. Right? So you have to depend, like how are the dependent systems going to interact with this. Not just dependent systems, it's also like your power users, like they are so used to like pointing their Excel at this database or access at their database and trying to do all kinds of crazy queries. They can't anymore because it's Mongo and they can't understand JSON or something like that. How do you give them the data that they need, right? looks like we are at a logical end here. Okay. Thanks, guys. Thanks for coming and wasting your perfectly good evening with me. All right. Thank you.